So in the first row of the Cayley table for the set M under multiplication, we have I, M sub 1, M sub 2, M sub 3, negative I, negative M sub 1, negative M sub 2, and negative M sub 3. Also in the first column, I, M sub 1, M sub 2, M sub 3, negative I, negative M sub 1, negative M sub 2, negative M sub 3. Now, M sub 1 times M sub 1 is negative I. M sub 1 times M sub 2 is M sub 3. M sub 1 times M sub 3 is negative M sub 2. M sub 2 times M sub 1 is negative M sub 3. M sub 2 times M sub 2 is negative I. M sub 2 times M sub 3 is M sub 1. M sub 3 times M sub 1 is M sub 2. M sub 3 times M sub 2 is negative M sub 1. And M sub 3 times M sub 3 is negative I. Now to complete the rows, we can take the scalar multiple, with that scalar being negative 1. In other words, we multiply each of the matrices in the row by negative 1, by the scalar negative 1, and so we have negative M sub 1, I, negative M sub 3, M sub 2, negative M sub 2, M sub 3, I, negative M sub 1, negative M sub 3, negative M sub 2, M sub 1, and I. And now to complete the columns, we multiply the corresponding matrices by the scalar negative 1. And so we have negative M sub 1, I, M sub 3, negative M sub 2, negative M sub 2, negative M sub 3, I, M sub 1, negative M sub 3, M sub 2, negative M sub 1, I, M sub 1, M sub 2, M sub 3, M sub 1, negative I, negative M sub 3, M sub 2, M sub 2, M sub 3, negative I, negative M sub 1, M sub 3, negative M sub 2, M sub 1, negative I. So we can see from the Cayley table that the operation of multiplication is closed over this set. We also see that there is an identity element. Each element has an inverse, which is a little harder to find, but each element does have an inverse. Now, in this table, there is no symmetry about the main diagonal, and so we see that the operation is not commutative. And again, the only thing that we cannot see from the Cayley table is that the operation is associative. But let's now verify that this is a group using the definition. So as the set M is closed under multiplication, the set M together with the operation of multiplication is a magma. As matrix multiplication is associative, this magma is a semigroup. There exists the matrix I in the set M such that for every matrix A in the set M, we have that A times I is the same as I times A, which is A. And so this semigroup is a monoid. And for every matrix A in the set M, there exists an inverse for that matrix also in the set M, such that A times A inverse is the same as A inverse times A, which is the matrix I, which is the identity for this structure. And so the monoid, namely the inverse of the matrix A, is the set A if A is plus or minus I, and is negative A if A is plus or minus M sub I. And so this monoid is a non-abelian group. Okay, so new example. And here we finally come to the quaternions. Let the set Q sub 8 be the set which contains plus or minus 1, plus or minus I, plus or minus j, plus or minus k, where I squared is the same as j squared, which is the same as k squared, which is the same as the product I times j times k, which is negative 1, where I times j is the element k, and I times k is negative j, j times I is negative k, and k times I is j. These elements are known, the positive elements are known as the quaternion units. They were discovered by the Irish mathematician William Rowan Hamilton. And so now we have enough to construct the Cayley table. Okay, so in the first row of the Cayley table for this set under multiplication, we have 1, I, j, k, negative 1, negative I, negative j, negative k. And also in the first column, 1, I, j, k, negative 1, negative I, negative j, negative k. I squared is negative 1, j squared is negative 1, k squared is negative 1. I times j is k. I times k is negative j. J times I is negative k. J times k is I. K times I is j. And k times j is negative I. So before we continue, notice that this 4 by 4 submatrix is identical to the 4 by 4 submatrix for the set M under multiplication. And so just as in this Cayley table, we're going to complete the Cayley table by filling in the rows, by multiplying the corresponding entries preceding in the same row by negative 1. And we're going to multiply, we're going to fill in the columns by multiplying the preceding elements by negative 1. And so the two tables are identical. So let's now complete the Cayley table for Q sub 8 under multiplication. So we have in the second row, negative I, 1, negative k, j. Then we have negative j, k, 1, negative I. Then negative k, negative j, I, 1. Now filling in the columns, we have negative I, 1, k, negative j, negative j, j, negative k, 1, I, negative k, j, negative I, 1, 1, I, j, k, I, negative 1, negative k, j, j, k, negative 1, negative I, and finally k, negative j, I, negative 1. So once again, the two Cayley tables are identical. So it's interesting to note that if we were to verify associativity, by direct computation, we would need to perform 8 cubed, or 2 to the 9th, which is 512 computations. But as the Cayley table for q sub 8 under multiplication is identical to the Cayley table for the set M under multiplication, we have that q sub 8 is isomorphic to the structure M. So since q sub 8 under multiplication is isomorphic to the structure M under multiplication, and M under multiplication is a non-abelian group, q sub 8 under multiplication is also a non-abelian group. And this group is known as the quaternion group. But more correctly, this is the group of quaternion units. The quaternions are actually a larger structure. So let's start looking at that. Let the set H be the set of all numbers of the form x sub 1 plus x sub 2 times I plus x sub 3 times j plus x sub 4 times k, such that x sub I is a real number. Notice that for every number h in this set, the number can be written in the form x sub 1 plus x sub 2 times I plus x sub 3 plus x sub 4 times I times j, since I times j is k. And so this set H is an algebraic extension of the complex numbers to include complex multiples of the number j. And so one representation of this set, which we call the set of quaternions, is as a two-dimensional space over the field of complex numbers. Now this set is also an algebraic extension of the reals to include real multiples of the numbers I, j, and k. And so another representation of the quaternions is as a four-dimensional vector space over the field of real numbers. So we will end here for today. Next time we will continue to look at the group structure of the quaternions, and we'll actually define it in an analogous way as we did for the complex numbers. And then we'll continue to look at finite groups and then move on to the larger class of cyclic groups. So I hope you have enjoyed the 12th lecture. Thanks for watching.